Good afternoon, everyone. Today, our group from Section B will be presenting our present project for the Digital Logic and Circuit course. Our project is a parking control system, and our course teacher is Mr. Rithon Fayaz. So, throughout this presentation, we will walk you through the key components, logic design, internal architecture, hardware implementation, and code behind our system. So, let's begin. So, here are some few steps for the parking control system. So, we move on to next slide, which is comparison. So in this section, we analyze different register configuration from group member IDs and their impact on digital to analog converter DAC circuits. So the observations, like some of the group members used a low value register, while other used higher value registers. The slight and some of them have slight imbalance between paired register RARC and RBRD. Some used 3-bit DAC, unlike others, and some of them use 4-bit DAC. It's like similar trend to previous entires. We slightly reduce RA and RC, and some wide resistance rates suggest less linearity or custom scaling. So this comparison highlights the role of register values in shaping the functionality and efficiency of DACs. So next slide, in a block diagram, flow diagram, and internal architecture, in our design, we defined a maximum number of cars as 11 based on the group members' IDs, and the system uses 4D flip-flops to represent a binary count from 00000 to 1011, and the output from Q0 to Q3 reflects the current number of cars, and AND gate triggers increment while NOR gate triggers decrements. And about the counter clock, the QA toggles every clock pulses, while QB toggles every 2 pulses, QC in every 4, and QD every 8 pulses. So one full cycle takes 16 pulses, returning to 0000. This structure ensures reliable count tracking through basic sequential logic. So in the next slide, we use two 555 timer circuits, one in stable and one in monostable mode to drive the displays. Circuit one is stable mode, while timer circuit two is monostable mode. So here we calculate the values, and we calculate RA and RB, and RC and RD both. The value of RA is 1616 ohm, so we used a standard value of 1.6 kilo ohm, and RB is 2078 ohm, so we used a standard value of 2 kilo ohm. And next slide is about state diagram and state table. Here we outline the state behavior of the FSM in our system. The state machine moves from S0 to S7 with each state representing unique binary count from 000 to 111. Transition from S0 to S3 correspond to output A equal to 1 and B equal to 0 from S4 to S7. The value shift to A0 and B A equal to 0 and B equal to 1. And this model ensures control state transition aligned with clock timing. This is the Verilog HDL code. And finally, let's address limitations and future scope. To support larger parking lots. We can increase the counter size to 8-bit to accommodate more vehicles. Like we use 8-bit counters, there can be room for 255 cars. While if you use 4-bit, there can be room for only 15 cars. So instead of static message, we can use a LED matrix displays for dynamic and multi-language output. Integrating a microcontroller allows for more flexible control, logging, and even remote and monitoring. Uh, this concludes our presentation on the digital logic circuits and parking control system. We have demonstrated how a fundamental digital components, flip-flops, counter, comparators, 555 timers, and state machines can come together to solve real-world problems efficiently. Thanks for your attention. We are now open to any question. Thank you so much.
Assalamu alaikum everyone and good morning, sir. Uh, my name is Jubar Ahmed. We are from section B. Our course teacher name is Ethan Fayas. Today we are going to present our project on a digital parking control system developed as part of the digital logic and circuit course. Here are the group members of our group: MD Jubar Ahmed, Mirza Sultan Yasmin Shobha, and etc. etc. Here is the next slide. Step for parking control system. Use a keypad to set the maximum value parking space. Entry and exit sensor detected vehicle entry and the parking area. And here the if counter current count greater than less than max number, then will be space value. Here's the next slide of comparison. Comparison by ID numbers of our group. Here are the number of bit. First of all, there are 4 bit. Then second is 4, third is 3, and 4, 5 is also 4. And there are the comparison of RA, RB, RC, and RD. The next slide is observation. First of all, there is low value register set for in the ID number of 23-50-318 suitable for low voltage high speed application due to minimal resistance. Balance RA, R and RC as well RB and RD values closely matched. Here also the observation part. And the next is comparison description. Why the RA, RB and RCD value are different for full or blink and space available. Here is the block diagram, flow diagram and internal architecture. Here are the A, B, C, D, E, F, G, H is based on our ID number 23503181. Maximum cars is based on by counted by our ID numbers 11. And here we used 4D flip-flop store counters as Q3, Q2, Q1 and Q0. We use I use 4-bit binary counter. We also used in 2 7 segment display using 2 55 timers. And here are the value of RA, RB, and here are the value of RC and RD. We used state diagram. Here is the Verilog HDL code based on ascendant. And limitation modification and impact of changes. Limitation counter and logic system. 55 timers display circuit. Limitation for 4-bit is 7 to 15 cars, and no overflow, underflow, handing incorrect count if too many enter and exit occurs. And here is the modification and impact of changes. We use higher bit to execute larger number of cars. Replace 55 timers. Programmable digital logic. We should dynamic configuration through comparable programmable hardware. That's all, everyone. Thank you so much, sir. Assalamu alaikum.
Assalamu alaikum. Myself Shahjadullah Chaudhary, and I will be discussing about our presentation on digital logic and circuit. So our topic is parking control system, and these are the steps. We use a keypad to set maximum available parking spaces, and we use some sensors to detect the entry and the exit of the vehicles. Then we use up-down binary counter to keep track of the number of cars. Then we implemented the counter using a flip-flop. These are the comparison of our group members using our calculation in all. Most of our members used a 4-bit binary counter, except me. I need to use a 3-bit counter as I As for my requirement, my maximum car limit was 6. This is the 3-bit synchronous binary counter architecture. As we used a 3D flip-flop which count as Q2, Q1 and Q0. The output Q0 and Q2 represents binary count. The AND gate represents the increment and the NOR gate represent the decrement. The workflow means max number and the workflow means they are unspecified. And the clock pulse shows the Q0 toggle in every clock pulse, like after half clock frequency. The Q1 toggles after every 2 clock pulse, and finally the Q2 toggles after every 4 clock pulse, which means and finally 1 cycle completes in a clock pulse and it returns to 000. Here the 2-segment displays using 2 555 timers. One we use true circuit, one is in a stable mode, another one in unstable mode. The state machine cycles through 8 states from S0 to S7 using binary encoding from 000 to 111. States S0 to S3 correspond to output A1 and B0, and S4 to S7 A0 and B1 controlling parking system outputs. Each state transition occur based on clock timing parameters defined with TH for millisecond and TL for millisecond, creating a controlled timing environment. This is the Verilog SDL code for us FS implementation. The Verilog SDL code defines a finite state machine with 8 states organized into 2 groups. And here are some drawback and limitation of this parking system. Some limitations are the current 3-bit counter only supports up to 7 cars. The 7-segment displays have limited characters implementation, and 555 timer have limited precision for timing control. Modification for larger parkings are like increasing the counter size from 3-bit to 4 or 8-bit. We can use LED matrix displays for better messaging, and we can implement microcontroller based control for more flexibility. Assalamualaikum. My name is Mehdi Hassan Kaushik and I am now presenting the car parking system. Step of the parking control system: we use a keypad to set the maximum available parking space. Entry and exit sensor detect the vehicle entering on the parking area. Use up-down binary counter to keep track on the number of car. Implement the counter using D flip-flop. Now observation: my first member he used the low value register as my second member he used higher resistance value. Implements the possible power substance or lower current DAC circuit. Our third member only use 3-bit DAC. Unlike others, registers value are very close to the previous 4-bit entry. Suggested shared design methodology. Another slide which I discussed, block diagram or flow diagram, initial diagram, and internal architecture. Here we use 4D flip-flop. Output are Q0 to Q3 register binary count Here we use AND gate to increment and NOR gate to decrement. Overflow max number and underflow underflow is space available. And we use 4-bit binary repair counter. The input clock ripples drive the center. One pulse per increment. Q1 toggles every clock pulse. QB toggles every 2 clock pulse. QC toggles every 4 clock pulse. QD toggles every 8 clock pulse. One full circle completes in 16 clock pulse, returning to 000. Structural diagram. Structural diagram of 555 timer, which each state transfer occurs based on clock timing parameters with th 155 millisecond to 55 millisecond, creating the control timing event. The state machine cycles through the 8 state 15 S0 H0 to F7 using binary. We're using binary encoding 000 to 111 respond to output A1, A equals to 1, B equals to 0, and S equal S to S7. At first we saw S0 is going through S1, then S1 is going through S2. Again the timer is still continuing. At last, when it will go to S7, then it will again up to S0, again go to the S0 flip flop. This is my presentation.
From section B will presenting our project Digital Logic and Circuit course. Our project is parking control system and course lecture reference. Now, step 4, the parking control system. Use a keypad to set the maximum available parking space. Entry and exit sensor detect vehicles entering or parking area. Use up-down binary control to keep track on number of cars. Implement the counter using the flip-flops. Compare check if the current count equals number max. Next is comparison. The table shows resist value for different components. Each row represents component with a unique ID. The number bits it has the resistance value RA, RB, RC, and RT in. For example, the first component ID 235031881 has 4 bits resistors and value 1567 ohm, 2034 ohm, 1548 ohm, and 2256 ohm. Difference this value across different and component. Next is observation. The first item 235031881. This is low value resistor set suitable for low voltage high speed application due to minimal resistance balance RA and RC as well as RB and RD value. Next is comparison and description. The reason why RB, RC, RA, and RT value are different in each design is primarily due to variation in the required timing and functionality from the timing circuit. Each circuit is designed to perform specific functions such as continuously displaying full or blanking space available. And this difference display behaviors require different time delays. The timing is a 555 timer circuit operating in a stable mode is controlled by a resistor value RA and RB and a fixed capacitor. Next is block diagram, flow diagram, and internal architecture. 4-bit binary digital counter. The input clock impulse drives the counter 1 pulse per increment. QA toggle every 2 clock pulse, half clock frequency. QP toggle every 2 clock pulse, QC toggle every 4 clock pulse, and QT toggles every 8 clock pulse. Next, 2 7 segment display using 2555 trimmers. State diagram is state transition occurs based on clock timing parameters defined with TS195 MS and TL55 MS creating controlling time environment. And last, limitation, modification and impact of change. Thank you, everyone.